In this video, I am going to go over an example of verifying a logical equivalence, which will look like I don't want to say a simplified version per se, but an example of what proving will eventually look like, or at least a general idea of it. It will be more closely related, though, to geometric proofs in the sense that a geometric proof was complete where we would have whatever statements and the reasons for those statements in a table. The proof of this looks kind of like a table. So kind of less like what the ones we will be eventually doing, but at least looking kind of like it. Gives you that sense of it. Let me say that. So before actually I begin that, I did put up all of those different equivalences that we had from Theorem 2.1.1 from our textbook. But for this, we want to verify the logical equivalence of the negation of not P and Q and P or Q is logically equivalent to P. So we first start off with that same exact logical equivalent, the logical statement to the left in this equivalence, down over here. So the negation of not P and Q and P or Q, that being logically equivalent to the negation of not P or not Q and P or Q. And if we look down into our list here of different logical equivalences, the one that verifies this is all the way down here for the, De Morgan's law down here, where we kind of distribute the negation and change the operator inside of there, which is exactly what was done in this first portion of our statement, right? We basically distributed that negation through and changed the operation. So this is from De Morgan's law. De Morgan's law. And then our next line shows that logical equivalence of this statement that we just had with now P or not Q and P or Q. So that one, in essence, took that negation of not P and wrote that as P as just P. That's the difference between these two statements. And that one comes from this double negative law down here. So this is from the double negative law. Double negative law. The next aspect of that, moving down from here, is that we kind of, in the sense of a mathematical operation for it, basically factored out this P that is in both of these terms and put it outside of the operation here involving Q. So we have P or Q and not Q. And the law that did that was using this distributive law. Or I should probably say the opposite, and from the opposite direction, so essentially that factoring aspect. But that is, though, that distributive law. Distributive law. Then underneath that, we change that Q and not Q to this C indicating a contradiction, and that comes from one of the specific negation law. So that being down over here. Well, sorry, not that one. The one over here. With P and not P being logically equivalent to a contradiction, which is exactly what was done here. So this is with the negation law. Negation law. And then finally, that being logically equivalent to just P. And we could see down over here with the identity law, P or a contradiction is logically equivalent to just P. So that being one of these identity laws, so this would be the identity law. And then finally at the end, we have shown that logical equivalence, just restating the first line and this bottom line as therefore the negation of not P and Q and P or Q is logically equivalent to P, and then this box just symbolizing the end of this proof. And the reason why I say this is very similar to a geometric proof is because essentially we have all of our statements over here on the left and all of our reasons over here on the right. So we could essentially just split this up into two different columns, just like a geometric proof did, especially in high school. Thank you.